So welcome back. So as the semester winds down, like I said, we have only a small number of classes left. Hopefully everyone by now has taken a look at the homework. I mean, a reminder, it is due this weekend. And the next homework will be out basically on, it might even, hopefully if I'm ahead of schedule, it'll actually be out before the current homework is due. So hopefully it'll be out around Sunday. Again, it'll be just a small number of problems, and it'll be due, I think, during the exam period. So the reason for that is I want to give you guys plenty of time to do it. So if you feel like you need a little bit of extra time, it's okay. So I'll figure out exactly when that due date's going to be, but probably on the Saturday or the Sunday during exam week. Of course, you're welcome to turn it in. You'd be welcome to turn it in at any point, but I'll probably give you 2 weeks. The same thing is kind of true with the final. I think the aim is it'll be the same as the midterm, so a take-home final that I will hand out. I guess probably on the either December 4th or December 5th, and then give you 2 to 3 days to do it. So basically the same kind of format as last time. A small number of questions that you just kind of have to work through and answer some questions about, and then just submit the written answers online. So that's the plan so far. So admittedly, this is a little bit of an unusual semester. So if there's any feedback about that proposal, just let me know. I'm guessing that that's going to be fine for everyone, but for some reason it doesn't work, let me know. Any questions about the remaining timeline, or I guess the homework while we're here? No. Good. So please do start on the homework, though. It might take a decent amount of time to actually do, even though it's not. It was supposed to be a little easier because I gave you a compressed timeline, but still, please start on it when you get a chance. Okay, so last time we were talking about submodular optimization, just to show you kind of an example of where convex optimization arises in different contexts. So that was an example of applying convex optimization in a more discrete optimization setting. So there's a lot more interesting things to say about that. I just wanted to give you a little bit of a flavor. Like I said last time, there's a lot of applications in machine learning and artificial intelligence that are kind of based around the notion of submodularity. Today, I wanted to cover a topic that we could have covered earlier in the course, but I thought would be a nice thing to include now, because in some ways it reviews a little bit of the course material, as well as giving us a few new, one new algorithm, I guess, to think a little bit about. So this is the alternating projections algorithm. So it has a lot of utility in certain settings, although it's not necessarily the most popular algorithm for essentially computing, finding a point at the intersection of a collection of convex sets. So I'm going to motivate it a little bit, and we'll talk about the algorithm, and then we'll just do a couple quick examples that will involve the method of Lagrange multipliers to actually figure out how to do the alternating projections. So we have a little bit more practice doing the duality and Lagrange multipliers, while also adding a little bit to some of the discussion we would have had earlier in the course. Okay, so the motivation for something like this alternating projection method or some other variants of it are, so suppose we wanted to apply one of these descent methods for a constrained convex optimization problem that we've been doing basically the entire course now. If it's a constrained problem, we need to pick an initial point that satisfies the constraints. So, you know, on most of the homework problems and the exam problems, it was somewhat easy to pick a point that satisfied the constraints. But that's not always the case, actually. Sometimes one of the hardest things to do in an optimization problem is to just find a point that satisfies the set of constraints. So as an example, let's suppose we had a set of linear or affine constraints, you know, basically doing the same thing that we did on the homework, where we could use an existing LP solver to find a point that satisfies the constraints without even solving the problem. So let's suppose, for example, we've had a quadratic optimization problem. So we wanted to minimize a quadratic function subject to a set of linear constraints. Well, or affine constraints, we could find a point that satisfies the affine constraints just by solving a linear programming problem, without actually solving the full quadratic programming problem, let's say, that we're actually interested in solving. Does anyone see how you would do that? Right, what I mean, like, generally is if I have an optimization problem like minimize over x of f of x, right, subject to ax less than or equal to b, and I want to find a point that satisfies ax less than or equal to b, right? So I just want to find basically a starting point for some, you know, optimization procedure. I can find such a starting point using linear programming. So how would I do that? Thoughts? No thoughts. I've asked a question too early in the morning. Well, if you were just looking to find a point that satisfied the constraints, you can solve any optimization problem you want. So as an example, if I wanted to use a linear programming solver, I might just solve the following optimization problem. X and Rn, ax less than or equal to b, where c here in the linear objective, c is just some random vector. Doesn't even matter what it is, because no matter what c you pick, the solution to this linear programming problem will be something that satisfies ax less than or equal to b. Right? So if there is a solution, no matter which vector c you pick, that will just identify one of the vertices of the constraint set, and it'll be returned. Right? So the only time something like this wouldn't work is if you have an unbounded constraint set, and you know, maybe something runs off to negative infinity. But assuming that the problem is bounded, you can just pick basically a random, you know, random linear term for the objective, and then solving that optimization problem would give you a point that satisfies ax less than or equal to b. So that's fine, I guess, for like a set of affine constraints, right? I mean, you could generalize this, right, to if you had more complicated constraints, just finding a point that satisfies the constraints, you could formulate it as some optimization problem and then try to solve it. But I guess the question that we're going to try to answer today is there a somewhat better way to do this, right? Because solving a complicated optimization problem just to find an initial point might not be so great. All right, is the motivation clear? So what we're really trying to do here is just find initial points for our descent methods under the assumption we're minimizing a function with respect to constraints, and that the constraints might be complicated, but we'd like to find just some point that satisfies the constraints. Okay. So the algorithm is actually based on the idea that the intersection of convex sets is convex. So we've been using this observation for a long time now, basically implicitly. So anytime we wrote down a convex optimization problem that had multiple constraints, what we really meant is that all the constraints needed to be satisfied at the same time, which is equivalent to basically taking each one of the constraints. They were all correspond to convex sets, and basically taking the intersection of all of those convex sets. That was the constraint set for our convex optimization problems. So the problem of interest, at least in today's lecture, is going to be, given two or possibly more convex sets with a non-empty intersection, can we find a point that's inside of both of them? So pictorially, I don't know, here's some convex set C, here's some convex set D. All I would like to do is find a point that simultaneously satisfies both C and D. So this is if it was just a single set, this is actually, a problem that we looked at before, right? If we wanted to find just a single point, a point, for example, that just satisfied constraints they correspond to the convex set C, we could have done that just by taking some other point Q and projecting it onto the set C. That would have been our strategy to find something that satisfied the constraints, right? We would take something that doesn't and project it onto the set of constraints of interest. Now, obviously, that's not going to work here. If we want to find point X between C and D, right, and I just take some point Q and I project it onto C, right, I'll end up with a point that could be over here in this region that satisfies the constraints for the set C, but not the set D. And similarly, right, projecting onto D, right, may or may not actually give me a point that ends up in this intersection. In this case, it looks like it might give you a point that ends up in the intersection. But there's no guarantee in high-dimensional spaces if you just project onto one of the sets that you'll get lucky, right, and end up at a place that satisfies all the constraints. So the idea behind the algorithm we're going to talk today is exactly this, right? To find a point in the intersection, we're going to repeatedly produce a set of projections. The intuition is that basically every time we do a projection, we kind of get closer to our target. So sort of in pictures, it is true that if I take the point Q here and I project it onto the set C, that I don't end up with a point in the intersection of both C and D. However, I've gotten closer, right? This point here, I don't know, let's call it Y, right? Y is closer to the intersection than Q is. So we actually did make some progress, right? Even though it might not, be as much as we would want, right? We definitely made progress. We could actually see that if I then took the point Y and projected it onto D, right, I would end up with a point that, right here, that was actually in the intersection of the two sets. Okay. Now, of course, one of the assumptions in this is going to be that our sets are closed, because we'll only ever, as we can see from the pictures here, we'll basically only be able to converge to points on boundaries of the sets. So some of our sets are open. We won't find something that satisfies the constraints necessarily. Okay. Question about the problem of interest? So the procedure or one procedure that can be used to solve this problem is something called the alternating projection method, and it's actually quite an old method. So it's been studied for many years, and was one of the earlier methods as part of convex optimization. Again, because it's sort of a natural problem, right? You need to find something that satisfies a set of constraints. It seems natural that you'd consider something like this method. So the method works like this. You just pick an initial point. I don't know, let's say x naught. Just like all of our strategies, we can assume that it's just picked at random from some set. And then you just iterate, for t equals 1 to until you get tired. You set yt to be the projection onto the set C of xt. Right, so originally we'd start off with x0, and then we'd get y0 by projecting x0 onto C, and then we get x1 by projecting y0 onto D. And then we just keep iterating this process, right? Like I said, until we get tired, we just keep doing it. So this procedure actually is guaranteed to converge depending on conditions on the two convex sets C and D. You can actually prove that this thing makes progress and eventually, and actually is converging to a point in the intersection. The proof basically argues that, just like I showed in this picture, that you are effectively always making progress towards getting closer to the intersection every time you do one of these projections. One thing that's worth pointing out about this approach, though, is that it doesn't necessarily guarantee that there exists a finite t such that the tth iteration of this procedure will actually be in the intersection, right? It could be a situation where you're just converging to that point and you don't actually, any finite iteration is getting closer to that point, but it's not necessarily, but no point by itself will satisfy all the constraints exactly. So here's an example of what this might look like. Oh, I forgot to put the citation for this image. So if we start at a point, let's say x0, and let's assume it's in the set C, it wouldn't have to be, right? We could always assume that we start with a point in the convex set C. If we don't, right, we could just do our first step could just be projecting x0 onto C. It doesn't matter. We can pick any point we want to start with. Right, we then project x0 onto D, and that gives us the point y0. And then we project y0 onto C, gives us the point x1, and x1 onto D, which gives y1, and so forth. So you can see if this process continues, it's just going to keep zigzagging back and forth between these two sets until eventually it gets close enough to x star that due to numerical precision we can't tell the difference between them. So this procedure in this particular case effectively converges to that top point x star, which is in the intersection of these two sets. Questions about the procedure? Like I said, this picture is a good example, right? At no point in the iteration, like technically, right, do you ever actually end up with a point that is simultaneously both in C and D. But as the number of iterations increases, right, you're getting arbitrarily close to the point x star, like so much so that at some point you won't be able to tell the difference, right? In fact, this procedure will likely converge to something if you were to actually run it for these two sets. Questions so far? Okay, so the idea can be generalized to more than just two convex sets. We could have k convex sets, and if we want to apply this for more than two, the strategy is exactly the same, right? We would pick just some initial point, and then we would iterate, for t equals 1, 2, and again until we get tired. We would just select one of the sets from 1 to k, let's say S, and we would just project our current iteration onto the set CS, and then just repeat. Okay, so we just keep repeatedly projecting xt onto a new set until we get tired. How should we pick the S here? Well, it doesn't really matter. You could use like a round robin procedure, right, where you'd start off with S equals 1, then S equals 2, then S equals 3, all the way up to S equals k. and then reset back again at s equals 1. You could do that. Sort of like, the strategy that we talked about for like the stochastic gradient method, right? You could always do round robin, or you could just pick, one of the sets at random and project onto it, right? So just, pick a number between 1 and k, an integer between 1 and k uniformly at random, and then project onto which the set corresponding to the integer that you picked. The intuition behind this procedure is still the same, right? The intersection now is given by C1 intersect CK. The idea is that every time you project onto one of these sets, you're getting closer to their intersection. Okay, so for the remainder of today, then I just want to do a couple examples of how you would actually use this in practice. Just like the projected gradient method, right? This procedure will be particularly efficient, at least to implement, right? If the projections, right? If each one of these pieces is easy to compute, right? So the intuition here is that maybe we have a complicated constraint set, but that the projection onto we can formulate that constraint set as the intersection of a bunch of constraints, and we can easily compute the projection onto each one of the pieces. So here's an example, right? Going back to the set of constraints that we were talking about at the beginning of today's class. Suppose we had a constraint of the form ax less than or equal to b, and I wanted to apply this alternating projection method to find a point that satisfies ax less than or equal to b. Now, in general, ax less than or equal to b, right, can be a complicated set, right? And it just describes some set of linear constraints, right? And in the projection onto this set, right, looks something like this. So as we would have done previously, right, we would have solved we would have found such a point by solving some optimization problem. Right now, I'd like to apply this alternating projection method, and it could be, for example, that it's too difficult to figure out how to project onto the whole set ax less than or equal to b. But if we divide it up into individual pieces, the projection gets a lot easier, right? As an example, right, there's 4 constraints here. Each one of them corresponds to an inequality, right? That, for example, that first line corresponds to an inequality, a linear inequality that says that that the first convex set corresponds to this region. The second convex set, for example, this one over here, corresponds to this region, right? So it's just a collection of hyperplanes. They divide space into a bunch of distinct regions, and then we compute their intersection. Okay. Gives us this interior set. So really, the projection onto this, if we wanted to apply this alternating projection strategy here to find a point in the intersection of these sets, right? Each one of our operations just requires us to project onto a single hyperplane, effectively, in in n-dimensional space. So let's solve that optimization problem to see what we end up with. So our goal here is to project onto this constraint set, but we can formulate this a little bit more simply. Let's suppose that we just had a single constraint, right, of the form A transpose X plus B. A transpose X is less than or equal to B, right? So in the original problem, right, A would have been an m by n matrix, and B would have been an n-dimensional vector. Here, let's just take the simpler case where just B is a single real number, and A transpose is a real n-dimensional vector. Okay. The nice thing about the method of alternating, this alternating projection method is that the general case, right, where we have m of these kinds of constraints, is no more difficult, right, because it would just involve us projecting onto one constraint of this form at a time, right? The total set of inequalities we get from this looks something like, we take the first row of A and multiply it by x, and that should give us, that should be less than or equal to b1, right, etc. Right, so we get a series of m inequalities instead of just a single one. But the alternating projection method, right, it just requires us to be able to project onto one of these each in turn. So to compute the projection onto this set, the optimization problem we need to solve is, right, so given some point q in, let's say, Rn, our goal is to find an x in Rn such that the distance between q and x is as small as possible, and x satisfies the constraints. So A transpose x has to be less than or equal to b. And for some reason, I tilted down my my screen because there's going to be more writing, and for some reason it's now writing in some weird wavy way. So apologies. Okay. So this is just the standard projection procedure, right? We have a constraint, we have one linear constraint, and our goal is to project onto that linear constraint or affine constraint. So this optimization problem is relatively straightforward. Why? Because it's a constrained optimization problem with one constraint, right? For example, right, it might be somewhat tricky to solve, in this primal case, but we know if we would construct the dual optimization problem, the dual optimization problem would also be a quadratic optimization problem with a single constraint, and it'll also have a single variable, right? So if we construct the dual optimization problem here, it'll be easy to find a solution. Moreover, we know that the primal and the duals have to agree here because this optimization problem satisfies Slater's condition. There's always something that strictly satisfies this affine inequality. So we can just apply the method of Lagrange multipliers to actually just solve this problem, right? We can figure out exactly how to compute an x that's a projection onto this set. Okay, so let's just go through the procedure again. Like I said, this is, I picked this today partly because it's sort of an interesting algorithm that we haven't really seen before, but also gives us an opportunity to practice some of our some of the theory that we've been deploying in the course. Okay. So to use the method of Lagrange multipliers, I do the same thing that I always do. I need to add a Lagrange multiplier for each constraint. There's only one here, so I'll add a Lagrange multiplier lambda. It corresponds to an inequality constraint, so it has to be greater than or equal to 0. So I end up with the following Lagrangian. L is a function of x and lambda. So again, x is in Rn, and lambda is just a single real number that has to be greater than or equal to 0. And it looks like 1/2 q minus x squared. So I take the objective function and add to it a Lagrange multiplier times the constraint. Remember, the constraints have to be in standard form, so I have to write it as some function of x less than or equal to 0. So that's A transpose x minus b. Okay. So now, because my constraints are convex, in fact, they're affine, and the objective function is convex, the Lagrangian I end up here is a sum of convex functions, which is convex. So if I want to construct the dual optimization problem, I simply need to take the partial derivatives of the Lagrangian with respect to x, set them equal to 0, and solve. Okay. So I do that. The partial derivative of L with respect to, I don't know, the kth component of the vector x. So these are partial derivatives, not 2's. There we go. Looks like, well, the partial derivative of the first term with respect to xk looks like xk minus qk, plus the partial derivative of the second term with respect to k looks like lambda ak. And I set this equal to 0 and solve, which tells me that x should be equal to what? Lambda a or q minus lambda a. Okay. I can then take this back in. I can take this and plug it back into the objective to get the dual function. So that gives me that g of lambda is equal to, well, 1/2 q minus lambda a is just lambda a, 2 norm squared, plus lambda times a transpose x looks like a transpose q minus lambda times a transpose a, and then minus lambda b. So I've got a 1/2 lambda squared norm of a squared minus lambda squared norm of a squared. So with a little bit of simplification, this gives me minus 1/2 lambda squared norm of a squared plus lambda times a transpose q. It shouldn't be a lambda there. Minus lambda b. Okay. And again, the dual problem we have that lambda has to be greater than or equal to 0. But now the dual is an easy optimization problem. Why? Because it's an optimization problem over a single constraint with a single variable. And the constraint is easy. It's just that the variable has to be greater than or equal to 0, right? So we get two cases then, right? Either when we take the derivative of g with respect to lambda and set it equal to 0 and solve, we get a lambda that's greater than 0. Or the solution is attained at lambda equals 0 or lambda equals infinity. Right? We can see that the solution, we're maximizing the dual, right? The solution can't be attained at lambda equals infinity here because as lambda gets larger, this first term just becomes arbitrarily small, right? And it's growing much faster. It's going much faster to negative infinity than any of the other terms, so it'll dominate. So the solution will either be at lambda equals 0 or at a place where the derivative is equal to 0. So, dg d lambda, again, right, is just minus lambda times the norm of a squared plus a transpose q minus b, which tells me, and I set this equal to 0 and solve, which tells me that the derivative will be equal to 0 when lambda is equal to a transpose q minus b divided by the norm of a squared. So the solution then is either lambda is equal to this thing, if it's greater than or equal to 0. So this thing being greater than or equal to 0 should correspond to the constraint being satisfied. So if this is greater than or equal to 0, or constraint being violated, right? So if A transpose Q minus B is will be greater than or equal to 0 whenever A transpose Q is greater than or equal to B, right? So it'll be the constraint in the opposite direction. So we'll return this if the constraint is violated and 0 otherwise. I'd write that up there, but I'm out of space on the edge. Okay. So then same thing, right? I can then use the fact that strong duality holds here in order to solve for x. So we already saw that the root of the Lagrangian with respect to x, we should have x, the optimal x should be equal to q minus lambda a. So then I just plug in that lambda that I just solved for over there. I don't know, let me just call it lambda star, and that's the solution. That's the projection onto the set, right? Where lambda is given by that this formula over here. Okay. So while it might have been difficult to compute to find a point in the intersection of this set to begin with, there's basically a closed form solution to project onto a single constraint of this form. And the alternating projection algorithm, right, would just project onto this one. Like there's m constraints here. It would project on, say, the first constraint, right, which could be done in closed form, then project on the second constraint, which could be done in closed form, third constraint in closed form, etc. Right? And I just keep doing this until I get tired, or I end up with a point that satisfies all the constraints. Questions about this? So we're gonna do a couple more examples, but I want to pause here because the procedure for the next two examples is exactly the same as the procedure here. So questions? The conditional for the first part of lambda. Can you rephrase what you mean by that? Like in what's in the blue box? You mean like what's the condition for the lambda to be equal to the first thing? Right. It'll be equal to that whenever that thing is greater than or equal to 0, which is equivalent to saying that A transpose X is greater than A transpose Q is greater than B. Right, because if you take the derivative, right, so we took the derivative and solved, right, if we end up with a lambda that's greater than 0, that has to be the minimum, right? If we don't end up, if lambda doesn't satisfy the constraints, then the minimum will have to be attained somewhere. I mean, the maximum will have to be attained somewhere else, namely at lambda equals 0. Okay. Good. Other questions about the procedure? So this is much easier, right? Because it allows us to take like a really complicated constraint set, turn it into a series of hopefully much simpler constraints, right? And just project onto the individual easier pieces. Right. Good. Now, the caveat with all of this, right, is that, let's scroll back to the picture for a second. This original picture, right? This iterative procedure is not equivalent to projecting on, it's not like projecting onto the intersection, right? These two things are not the same, right? Here the projection on the intersection versus this iterative procedure might not result in the same point. So we can't use this to solve necessarily, right, projection onto a, projection onto the intersection, right? It just allows us to find a point in the intersection. Okay. Other questions about this example before we do another one? The second example I want to do is uses a much more complicated set of Lagrange multipliers, which is why I wanted to save it. Well, it's a matrix example. just to do another one of those. Okay. No questions? Okay. All right, so let's take a look at another example. So here's an example from the midterm. Let's suppose that we wanted to project onto the set of n by n doubly stochastic matrices. Well, not really a projection, right? We just want to find something that simultaneously satisfies all these constraints. So remember, a matrix is doubly stochastic if it's non-negative, and each of its rows sum to 1, and each of its columns sum to 1. Now, it's easy to produce such a matrix. Let's suppose that you didn't want to think about it, and you just wanted to find something that satisfies these constraints. Let's say because you wanted to solve some optimization problem over these matrices, and you wanted to pick a starting point to satisfy the constraints. We could apply the alternating projection method here as well. So again, to do this, we need to compute projections onto the individual pieces, right? So here there's one constraint for every row. Here there's one constraint for every column, and here there's a non-negativity constraint that we would also have to check. We know how to compute we know how to do the projection onto the non-negativity constraint. If you give me some matrix A, and I want to project onto the set of all things greater than or equal to 0, we know that the solution to this is just to set the ith entry of this matrix is just equal to the maximum of 0 and aij. Right. So if a is smaller than 0, we just set it to 0, and if aij is greater than 0, we leave it as is. So we already know how to compute that projection, right? We did that earlier in class. So that's an easy one to project onto, right? We just need to figure out how to project onto these sum to 1 constraints. And then just alternating between projecting a row and a column onto the constraint set in order to apply the alternating projection method. So what that means is we need to solve this optimization problem. We want to minimize over x in our, that should be an n there, of the difference between q minus x squared, where again q is some given point in n-dimensional space that doesn't satisfy the constraints. So, or may or may not satisfy the constraints. So in this particular case, right, we'll always be choosing either a row or a column of the matrix A and projecting them one at a time. So we just need to, so assume that Q is just either a row or a column of A, right? We'll project that row or that column, and then we'll apply the projection procedure to the next thing. So note here that right, that the row constraints and the column constraints are all independent of each other. What I mean by that is that look at all the row constraints, right? Each one of them, right, deals with a different row. They don't overlap. There's no variables shared in common, between the block of row constraints. Same thing with the column constraints. There's no block of variables shared in common between the column constraints. You just basically solve them one at a time. Okay. We can solve them all together too. The thing about the alternating projection method is you can project onto as big or as small of a block as you want. Here, it's easiest to solve this optimization problem, and it's pretty similar to what we just did. So we'll solve this and just repeatedly apply the operation until we end up with something that hopefully converges to a doubly stochastic matrix. So solving this optimization problem is exactly the same procedure, right? Again, it's a very easy optimization problem. Although this is a complicated set of constraints, this optimization problem is easy to solve, right? Because it doesn't involve, it only involves projection onto this sum to 1 constraint. Okay. So again, right, we would, to solve it, we use the method of Lagrange multipliers. Again, we know things will work out nicely here, as long as there is a solution to, the sum over all I of xi equals 1, which of course there is, then strong duality will hold with whatever the dual problem is here. We know the dual problem will have exactly one variable, and it will be unconstrained. So the dual problem will just be a quadratic minimization problem. We'll just be able to solve directly for the dual variables, plug the, and then use the solution for the dual variables to find the primal variables. So basically the same procedure as last time. Very much the same. Oh, let's put a 1/2 there too, make my life easy. So 1/2 norm of q minus x squared plus our constraint, which is our Lagrange multiplier times 1 minus sum over all I of xi. Again, taking partial derivative of L with respect to x, I get xk for some k. I get xk minus qk plus nu, which tells me that x should be equal to or minus nu, which tells me that x should be equal to q plus nu times the vector 1, the vector of all ones. Again, plugging that back in, I get that the dual problem g of nu, well, I'll get 1/2 q minus x, which is q minus nu times 1. So this would be nu squared times the norm of 1 squared plus nu times 1 minus, here's the sum over all xi. So xi is equal to qi plus nu. And that's it, right? I mean, it's just some optimization problem, right? So I get a nu squared times, so this first term it just looks like 1/2 nu squared times n plus the minus this plus nu minus the sum over all I, nu times sum over all I of qi minus nu squared. Times nu squared times n, right? Because I have a sum over all I here. So there's n of them, but with a minus sign in front. So I get a minus nu squared n. So that cancels out with the first term. So just grouping terms together, I get a minus 1/2 nu squared n plus nu. Oops, and that's a little close together. Minus nu. Minus nu times the sum over I of qi. And again, so strong duality holds, right? And this is just a convex optimization problem without constraints. So I can directly solve for nu, right? Taking a derivative of g with respect to nu, which is too close to the bottom of the screen. I get what? Minus nu times n plus 1 minus the sum over all I of qi has to be equal to 0, right? Which tells me that nu should be equal to 1 minus the sum over all I of qi divided by n. So plugging that back in, I get that the projection then should have the optimal solution x star is just equal to is equal to Q plus 1 minus the sum over y of Qi over n times the L1's vector. So again, right, in this procedure, right, I would just iteratively apply this, to where the vector x would just be either a column or a row of the matrix A, and just iteratively just keep updating, right? Pick some row or some column, project onto it, get this new solution, and repeat. Okay. And of course, right, I have to alternate between that and projecting onto the greater than or equal to 0 constraint. And in the end, if we keep iterating this procedure, it will the resulting matrix, right, will be approaching a doubly stochastic matrix. So there's two examples now, right, where it's relatively straightforward to sort of solve these projection problems, right? In fact, many of the convex optimization problems we saw, right, like part of the difficulty, right, with computing something that satisfied the constraints, right, would have been that we needed to satisfy all the constraints at the same time, right? And the same thing with computing the projection, right? Projecting onto the set of all constraints, right, might be difficult, again, because the aim is, we have to find something that satisfies all the constraints at the same time. Whereas like this alternating projection thing, we can just take one constraint at a time, right? Every time we apply the method of Lagrange multipliers with a single constraint, right, we're going to get a dual problem that's basically easy to solve because it's only going to involve a single variable, right? Perhaps with some constraints, right? But that tends to be a much easier problem, right? And in fact, many times will admit a closed form solution. We just solve that problem, and then we just alternate between projection onto these single constraints at a time in order to find a point that satisfies all the constraints. Questions? I'm going to do one more example that's maybe slightly more interesting. I don't know. Again, just to sort of drive the point home that this is sort of an easy procedure to implement in practice. But I'll stop here in case there's any questions. We saw too here, right, that in both of these cases, right, this gives us some nice simple examples of the method of Lagrange multipliers, right, because we only end up with like univariate duals. They're not anywhere near as complicated as the kind of duals that we have been seeing in the course, right? These are very simple optimization problems. And projections will always have quadratic objectives, right, with respect to some, because of the nature of projection defined with respect to Euclidean distance, right? So really, how complicated the dual problem will be will just very much depend on what kinds of constraints that you actually have. If they're linear like this, they're pretty easy and have a closed form. If they were something more complicated, it might be more complicated. Good. No questions? Okay, good. Well, I hope there's no questions because it's just so easy, and not that it's so hard. But I trust you guys to ask questions if you have them. Good, right? I mean, I hope that it's like a sort of a simple application really of the method of Lagrange multipliers, and it's very easy to implement this in practice. Okay, so then one final example, just to do an example that has some matrices or something in it. Let's take a look at projection onto semi-definite programming constraints. So, if you recall, right, semi-definite programming constraints look something like you're optimizing over some matrix that has to be positive semi-definite, subject to a collection of constraints that look like the trace of that matrix times some other matrix Ci should be equal to Bi. Right? So it's really these kinds of constraints that we have to look into. Again, this is a linear constraint, so we're an affine constraint, so we expect that like it should have a solution just like the these previous approaches did, right? So we'll do the method of Lagrange multipliers again and basically end up with like a similar answer, just with slightly different numbers involved and some weird matrix form, right? But we would expect that we end up with something very similar to what we ended up with here, right? Because this is a single constraint that says the sum of things has to be equal to 1. Here the constraint is more complicated, right? The trace, right, of A times some matrix C is equal to the sum over all ij. When A is a symmetric matrix, is equal to the sum over all ij of Aij Cij, right? So it's literally just a sum of individual terms, right? And we set that equal to Bi, right? So it's very much in the same form as the prior constraint, just now that this one involves matrices. So I thought I'd do one example of this because there was some confusion on the midterm with writing down the things with the matrix form. The first constraint, so there's two kinds of constraints here, right? There's this positive semi-definite constraint, right? And then there's these affine constraints. The positive semi-definite constraint, we already know how to project onto that, right? It was on the homework, but also we talked about in class, right? The projection onto the positive semi-definite matrices. You give me some matrix A that's symmetric but not positive semi-definite, right? The projection onto the set of positive semi-definite matrices just computes all of its eigenvectors and eigenvalues and zeroes out anything that has an eigenvalue smaller than 0. So the first constraint we already know how to project onto, right? It's really just this last constraint, this linear constraint, that we need to actually solve. And again, the procedure is pretty straightforward, right? The projection onto it. So again, there could be a whole collection of them. It doesn't matter. Let's just consider the projection onto a single constraint, right? So we want to minimize the difference between some matrix A and A minus our current iteration. So let's suppose that B, in this case, is our current iteration. And this is a matrix constraint, so we'll use the Frobenius norm, which is effectively just the vector 2 norm for the whole matrix. So we want to just find an n by n matrix that's as close to B as possible, while satisfying the constraint of the form, right? Trace A times C equals B. Or equivalently, right, to write this out, right, this is the same thing as writing, and we just write it out. The sum over all ij of Aij Cij should be equal to B. Okay, so again, I'm just going to apply the method of Lagrange multipliers. There's a single constraint, so I need one Lagrange multiplier. I have my primal variables A and my single Lagrange multiplier nu. And then I add the objective function A minus B Frobenius norm squared. Add to that nu times sum over all ij, Aij, Cij minus B. Again, compute the partial derivative of L. It's a convex function, so compute the partial derivative of L with respect to Aij. Gives me what? Aij minus Bij plus nu times Cij. Right, pretty similar to what we just saw. Setting that equal to 0, right, implies that Aij should be equal to nu times Cij minus Bij. Other way around. Bij minus nu times Cij. Okay. So I just plug that in to get the dual problem. So that gives me g of nu. Again, the dual problem is unconstrained here because this is an equality constraint. So g of nu, very similar thing to last time, 1/2 a minus b, but a is b minus nu times c. So b minus b is 0, and nu times c gives me a nu squared times the Frobenius norm of c squared plus nu times the sum over all I and j of Bij minus nu Cij times Cij minus nu times b. That's a nu there. So the second term here looks like minus nu squared c squared, right? So that's going to cancel out with this first term to leave me just minus 1/2 nu squared Frobenius norm of c squared. And then I have a plus nu times the sum over all ij of Bij Cij minus nu b. Again, this is an unconstrained optimization problem, right? I can just take derivatives and solve. Oops. And when I do that, right, I get what? That nu should be equal to the sum over all I and j of Bij Cij minus b divided by the norm of Frobenius norm of c squared. Plugging that value for nu in here gives me the optimal solution for A. Again, because I know strong duality holds, and that gives me the projection. So that's it. It's a really simple procedure, right? So now, even to project onto this more complicated set of constraints, which is a collection of affine constraints plus a positive semi-definite constraint, easy, right? I just keep iterating this procedure, right, until it converges. And all of the projections here can be done in closed form effectively, right? To compute the first one, I compute the eigen decomposition of A, or the singular value decomposition, well, eigen decomposition here. And then just for these other ones, I have a closed form solution that involves just computing this nu and taking B minus nu times C. Good. Questions about this? Or the procedure in general? Ooh, I should have pointed out, I guess. Yeah, not worth saying. Yeah. So this gives us this is a simple strategy to find an initial starting point for our optimization procedures when it's sort of non-trivial to find something that satisfies the constraints to begin with, right? When we don't have a good example of something that satisfies the constraints, or it can be somewhat difficult to come up with one. This actually really does happen, quite a bit in practice, right? If you were writing like a generic solver for something, and you needed to have in your whatever solution strategy you were using required you picking an initial point that satisfies the constraints. Say, for example, right, I think the constraint, like Newton's method with an equality constraint, for example, required us to basically start with something that satisfies the constraints, right? So this would be an algorithm you could use to start that procedure, right? Basically run this more or less to convergence. That gives us a starting point for equality constraint Newton's method. Okay. Questions about any of this? Good. Well, I hope this this is another couple of examples that we're all kind of similar, but kind of drive the point home that this is a relatively easy procedure to implement. We got just a little bit more practice doing the method of Lagrange multipliers, albeit in a very simple case. We'll do, like I said, so next week I think I'm gonna try to pick, topics, kind of similarly, right, that, will help us review a little bit of the course material, but maybe, we'll learn a little new thing here or there. Just sort of to drive, kind of just collect everything together and, kind of bring us to the end of the semester. Again, if there's a particular topic in convex optimization that we haven't talked about that you'd like me to say something about, you can, drop me an email or post on Piazza, and I'd be happy to talk about it. I mean, assuming that you don't pick something so hard that it takes like 8 lectures to cover, I'd be happy to talk about it. But otherwise, the plan for next week is basically to do a little bit of review of some of the material and just sort of wrap up the course. Okay. Any questions? We have like 5 minutes left. That's not really enough time to start another topic or anything. So we'll probably just stop here.